Okay, hi everyone. This is our automatic bottle opener presentation. My name is Rallian Herzog.
I'm Kyle Quetta.
My name is Takara Saigo.
And here we go. So for a little bit of overview, first things first, we're going to talk about the problem. Afterwards, we're going to talk about the mechanical and electrical design of our product. Then we're going to go a little bit into programming and simulation. And then we're going to finish off with what we learned. So sharing my screen. A little bit about the problem. Kids, elderly, and the disabled oftentimes have problems opening jars and water bottles. So there are things on the market that exist that incorporate mechanical advantage. As you can see, these grippers, but it still requires that the person be able to actually hold the bottle itself or the gripper and be able to twist it off. There are other things that are more automated in that the Robo Twist right here, it uses a motor to be able to twist off the cap. But in this case, it lacks sensors to be able to tell when the bottle it's squeezing is going to get crushed or not. So with that, we wanted to design a product that would incorporate both the use of sensors, motors, and mechanisms to be able to accomplish that issue. So looking at the solid model that we have, here's the assembly of our product. It can be broken down into three components. The first is the scissor lift mechanism, which is responsible for lifting the bottle into place. After that, we have the bottle gripper mechanism, which is simply in charge of grabbing the bottom of the bottle. Then we have the cap assembly, which is responsible for grabbing hold of the cap as well as twisting it half a revolution, basically just enough for the person to be able to remove the cap on their own without much force at all. And afterwards, the way it's supposed to work is that it releases the cap and then lowers back the bottle for the person to grab. Now we're gonna go into the electrical schematic, and Kyle is going to talk about that.
Thank you, Rallian. In terms of doing these electrical schematic for this particular project, we initially wanted to have it run by one feather, if at all possible, until further research with finding the correct motors, the amount of sensors we want to use, and the specific motor drivers that are able to run said motors that we chose. We opted for having it split into being run by two feathers instead of one. So instead, the upper assembly is run by one feather, and the bottom assembly is run by another feather. The top assembly is running the cap opener, or the cap twister rather, and the cap gripper, which is the set of claws you saw earlier. The motors are NEMA 23 motors that are all running off of it's a similar planetary gearbox configuration that are being driven by a Pololu high-power separate motor driver board. And they both have a 12-volt DC LiPo battery connected to it. On the lower assembly, there is a scissor lift that is powered by a linear actuator, and the bottle gripper itself, which are powered via another NEMA 23 motor and a Pololu hyper motor driver. The one thing I did forget to mention, though, is that the grippers for the bottle, the cap, and the base on the scissor lift all have a force sensitive resistor on them for one of two specific functions. For the scissor lift, it is meant to be able to tell the mechanism itself that there is something on the base, that there is something there for it to actually push up to, and for the everything to grip onto. For the grippers specifically, each of them have a they both have an individual sensor that allows them to be able to tell when when they're tightening their grip onto the bottle, or the cap rather, depending on which one is happening at the time, that if it is too much force, it'll stop instead of continuously going and possibly crushing the said container or the cap, depending on which one is operating at the time. And we also had to wire roughly three to four pins from each of the feathers for them to incorporate communication between each other, so that this entire assembly can operate smoothly and more often than not without slight error. That is the current electrical assembly of this, and I'll give it to Rallian for the code.
Great. So now that you guys have an idea about what the electrical components are and their function, I'm going to go ahead and talk about the coding that I did for the assemblies. 1 second. So I was responsible for the lower FM4E. And in this block of code, I'm initializing some of the sensors that Kyle talked about in his wiring diagram. The most interesting thing to note here are the pin done and the pin go initializations. And that basically allows me to know when the upper FM4E is done and also tell when I am done as well. So going down through the code, I'm just initializing the motors and the coils for the stepper motors as well. Going down here are some functions. So gripper high torque is basically running the stepper motor in a high torque configuration. And then here's a function where I basically grab the bottle or release the bottle, as well as a function for getting the voltage of the sensors. And over here, we can see minimum and maximum threshold. So in this case, a minimum threshold for the force sensor that's attached to the plywood base. That's going to tell when the weight of a bottle is there. And the max grip threshold is going to tell when the stepper motor should stop gripping so that the bottle doesn't get crushed. And then I'm going on to these last couple functions. It's basically extending the actuator and retracting the actuator when the function is done. Now going into the program itself, we basically have it so that every 5 seconds, it checks for the weights. But even before that, it waits for the button to be pushed so that it activates this while loop. After then, it gets the sensor data from the lift sensor as well as the gripper sensor, and basically waits for the bottle to be present onto the base. Once that happens, it will initiate the stepper motor to grab onto the bottle until the max grip threshold is met. Once that happens, the linear actuator will be extended until the limit switch is met. And once the limit switch is met, the bottle knows that it is in position to be grabbed by the cap. And that's going to tell this pin to go, signaling to the upper FM4E to basically grab onto the cap and twist it off. Once that's done, it's going to receive a signal from the upper FM4E that it's true. And once that's true, that basically gives us the green light to retract the actuator and then release the bottle for the person to grab. And this basically happens indefinitely whenever the person wants to press the button. Now, TK is going to go into the code for his upper assembly as well as simulating it.
Thanks, Rallian. So let me share my screen here. So this is the code for the lower assembly, which Kyle mentioned controls the bottle cap gripper and the cap twister. So because of the current predicaments, we weren't able to get the hardware to run this code. And so this code demonstrates it as a simulation. So as you can see here, if the simulation is false, it would have all of these pins, the pin go that would receive the signal from the bottom FM4E to start moving, and then pin done in order to, once the upper assembly is done, sends a signal to the bottom FM4E so that it knows when to go back. But these, all of these pins are simulated as Boolean value variables. And so in order to make these hardware ready, you would have to make simulation false and also name all of these pin variables or add dot values to them because to convert them from digital IO variables. And there's three big functions in this code. So procedure 1 deals with opening and closing the claw. This claw, or the claw, goes a certain distance calling back the step function, or that is over here. So this step function is a function that sends step signals or pulse signals to the stepper pin in order to move the stepper motor. And this function also simulates the analog value of the force sensor by acting as if there's a certain amount of force, and once there's a certain amount of force piled up after closing, it moves on. And then procedure 2 deals with the rotating cap twister, and like the previous procedure, it calls the steps function, but just for the rotating motor. And so we can see this code in action. Okay, so the claw is closing right now after it receives a go signal. And once the claw closes enough, it'll start moving on to procedure 2 and rotating, as you can see. And in reality, the pulses, like this is each pulse, it would be a lot quicker than as you can see here, but for the purposes of showing it in action, delayed quite a bit. And once it's done, at the end of the code, it sends a done signal to the bottom FM4E to indicate when it can go back to normal. And this simulation also has an error mode, which shouldn't move anything. So as you can see, nothing moved. There's no steps that went, as you can see here. There's no steps. There's no movement. So this is for when there's an emergency detected and everything just needs to stop. So with the code explained, I think we'd like to move to the learning points of this project.
Great. So yeah, now that we've figured out a little bit about the mechanical design, the electrical wiring, some programming, as well as simulating, we'd like to finish off with what each of us learned. Now, for me specifically, what I found most enjoyable to learn in this project was being able to interface between several electrical components, all to the same microcontroller. So with motor drivers and motors, as well as sensors, all outputting various voltages, it was interesting to see and overcome the challenge of getting those voltages to be able to be at the capability of the microcontroller. Now I'm going to hand it over to Kyle, and he's going to talk about what he learned.
Thank you, Ryan. In terms of what I learned from this project, the main takeaway that I learned from this was the idea that, and the idea and the amount of time that goes into making sure that everything in this mechanism and product will work properly and smoothly. Looking for specific specs of motors and the motor drivers that can power the said motors took a lot of time and research just in order to get to where we are right now. And given that, I'm going to give it to TK.
Thanks, Kyle. I think there was a lot of things I learned during this project, but I think the biggest learning point for me, or like one of the most important, impactful things I've learned, I felt like, is that the you can imagine you as you're making these schematics and designing your machine with various electronic components, you can't just make them up. They have to exist in reality. And if they do, you have to consider their actual cost, their availability. And it was surprising for me because I never really thought about that. I just I don't know what I expected, but I guess I expected that these perfect components would magically appear. It was a fun learning experience.
Great, and I think that about wraps up our project. Thank you so much for listening.
Thank you.
Thank you.